The Square Kilometre Array is a large multi-radio telescope project aimed to be built in Australia and South Africa. If built, it would have a total collecting area of approximately 1 square kilometre. It would operate over a wide range of frequencies, and its size would make it 50 times more sensitive than any other radio instrument. It would require very high-performance central computing engines and long-haul links with a capacity greater than the current global Internet traffic. It should be able to survey the sky more than 10,000 times faster than ever before, with receiving stations extending out a distance of at least 3,000 kilometers from a concentrated central core. It would exploit radio astronomy's ability to provide the highest resolution images in all astronomy. The SCAR would be built in the Southern Hemisphere, in sub-Saharan states with cores in South Africa and Australia, where the view of the Milky Way galaxy is best and radio interference least. Construction of the SCAR is scheduled to begin in 2018 for initial observations by 2020, but the construction budget is not secured at this stage. The SCAR would be built in 2 phases, with Phase 1 representing about 10% of the capability of the whole telescope. Phase 1 of the SCAR was cost-capped at €650 million in 2013, while Phase 2's cost has not yet been established. The headquarters of the project are located at the Jodrell Bank Observatory in the UK. Organization: the SCAR, a global project with 10 member countries, aims to answer fundamental questions about the origin and evolution of the universe. In April 2011, Jodrell Bank Observatory of the University of Manchester in Cheshire, England was announced as the location for the project headquarters. In November 2011, the SCAR organization was formed and the project moved from a collaboration to an independent, not-for-profit company. As of August 2014, the members of the SCAR organization are Australia, Department of Industry and Science; Canada, National Research Council; China, National Astronomical Observatories of the Chinese Academy of Sciences; Germany, Federal Ministry of Education and Research; India, National Centre for Radio Astrophysics; Italy, National Institute for Astrophysics; Malta, Institute of Space Science and Astronomy at the University of Malta; New Zealand, Ministry of Economic Development; South Africa, National Research Foundation; Sweden, Onsala Space Observatory; the Netherlands, Netherlands Organization for Scientific Research; United Kingdom, Science and Technology Facilities Council. Germany is a member, but on 5 June 2014 the Federal Science Ministry indicated its intention to leave the SCAR project at the end of June 2015. Description: the SCAR will combine the signals received from thousands of small antennas spread over a distance of several thousand kilometers to simulate a single giant radio telescope capable of extremely high sensitivity and angular resolution, using a technique called aperture synthesis. Some of the subarrays of the SCAR will also have a very large field of view, making it possible to survey very large areas of sky at once. One innovative development is the use of focal plane arrays using phased array technology to provide multiple FOVs. This will greatly increase the survey speed of the SCAR and enable several users to observe different pieces of the sky simultaneously, which is useful for monitoring multiple pulsars. The combination of a very large FOV with high sensitivity means that the SCAR will be able to compile extremely large surveys of the sky considerably faster than any other telescope. The SCAR will provide continuous frequency coverage from 50 MHz to 14 GHz in the first two phases of its construction. A third phase will then extend the frequency range up to 30 GHz. Phase 1, providing till the 10% of the total collecting area at low and mid frequencies by 2023. Phase 2, completion of the full array at low and mid frequencies by 2030. The frequency range from 50 MHz to 14 GHz, spanning more than 2 decades, cannot be realized using one design of antenna, and so the SCAR will comprise separate subarrays of different types of antenna elements that will make up the SCAR low, SCAR mid and survey arrays. SCAR low array, a phased array of simple dipole antennas to cover the frequency range from 50 to 350 MHz. These will be grouped in 100 meters diameter stations, each containing about 90 elements. SCAR mid array, an array of several thousand dish antennas to cover the frequency range 350 MHz to 14 GHz. It is expected that the antenna design will follow that of the Allen telescope array, using an offset Gregorian design having a height of 15 meters and a width of 12 meters. SCAR survey array, a compact array of parabolic dishes of 12 to 15 meters diameter each for the medium frequency range, each equipped with a multi-beam phased array feed with a large field of view and several receiving systems covering about 350 MHz to 4 GHz. The survey subarray was removed from the SKA1 specification following a rebaselining exercise in 2015. The area covered by the SCAR, extending out to 3,000 kilometers, will comprise 3 regions. A central region containing about 5 kilometers diameter cores of SCAR mid antennas and SCAR low dipoles. These central regions will contain approximately half of the total collecting area of the SCAR arrays. A mid-region extending out to 180 kilometers. This will contain dishes and pairs of SCAR mid and SCAR low stations. In each case they will be randomly placed within the area, with the density of dishes and stations falling off towards the outer part of the region. An outer region from 180 kilometers to 3,000 kilometers. This will comprise 5 spiral arms, along which dishes of SCAR mid, grouped into stations of 20 dishes, will be located. The separation of the stations increases towards the outer ends of the spiral arms. Key projects. The capabilities of the SCAR will be designed to address a wide range of questions in astrophysics, fundamental physics, cosmology and particle astrophysics, as well as extending the range of the observable universe. A number of key science projects that have been selected for implementation via the SCAR are listed below. Extreme tests of general relativity. For almost 100 years, Einstein's general theory of relativity has precisely predicted the outcome of every experiment made to test it. Most of these tests, including the most stringent ones, have been carried out using radio-astronomical measurements, by using pulsars as cosmic gravitational wave detectors, or timing pulsars found orbiting black holes. Astronomers will be able to examine the limits of general relativity, such as the behavior of space and time in regions of extremely curved space. The goal is to reveal whether Einstein was correct in his description of space, time and gravity, or whether alternatives to general relativity are needed to account for these phenomena. Galaxies, cosmology, dark matter and dark energy. The sensitivity of the SCAR in the 21 cm hydrogen line will map a billion galaxies out to the edge of the observable universe. The large-scale structure of the cosmos revealed will give constraints to determine the processes resulting in galaxy formation and evolution. Imaging hydrogen through the universe will provide a three-dimensional picture of the first ripples of structure that formed individual galaxies and clusters. This may also allow the measurement of effects hypothetically caused by dark energy and causing the increasing rate of expansion of the universe. The cosmological measurements enabled by SCAR galaxy surveys include testing models of dark energy, gravity, the primordial universe, fundamental cosmology tests, and they are summarized in a series of papers available online. Epoch of reionization. The SCAR is intended to provide observational data from the so-called Dark Ages and the time of first light. By observing the primordial distribution of gas, the SCAR should be able to see how the universe gradually lit up as its stars and galaxies formed and then evolved. This period between the Dark Ages and first light is considered the first chapter in the cosmic story of creation, and the distance to see this event is the reason for the Square Kilometre Array's design. To see back to first light requires a telescope 100 times more powerful than the biggest radio telescopes currently in the world, taking up 1 million square meters of collecting area, or 1 square kilometer. Cosmic magnetism. It is still not possible to answer basic questions about the origin and evolution of cosmic magnetic fields, but it is clear that they are an important component of interstellar and intergalactic space. By mapping the effects of magnetism on the radiation from very distant galaxies, the SCAR will investigate the form of cosmic magnetism and the role it has played in the evolving universe. Search for extraterrestrial life. This key science program, called Cradle of Life, will focus on 3 objectives: protoplanetary disks in habitable zones, search for prebiotic chemistry, and the search for extraterrestrial intelligence. The SCAR will be able to probe the habitable zone of Sun-like protostars, where Earth-like planets and moons are most likely to have environments favorable for the development of life. The signatures of forming Earth-like planets imprinted on circumstellar dust may be the most conspicuous evidence of the presence and evolution, and may even detect planets capable of supporting life. Astrobiologists will also use the SCAR to search for complex organic compounds in outer space, including amino acids. By identifying spectral lines at specific frequencies, the SCAR will be capable of detecting extremely weak radio emissions leakage from nearby extraterrestrial civilizations, if existing. Locations. The headquarters of the SCAR will be located at Manchester's Jodrell Bank Observatory, Cheshire, England. Suitable sites for the SCAR telescope must be in unpopulated areas with guaranteed very low levels of man-made radio interference. 4 sites were initially proposed in South Africa, Australia, Argentina, and China. After considerable site evaluation surveys, Argentina and China were dropped and the other 2 sites were shortlisted: Australia and New Zealand. The core site is located at the Murchison Radio Astronomy Observatory at Mildura Station near Buladi in Western Australia, 315 kilometres northeast of Geraldton, on a flat desert-like plain at an elevation of about 460 metres. The most distant stations will be located in New Zealand. South Africa. The core site is located at 30.72113000 degrees south, 21.411127 degrees east, minus 30.72113000 21.411127 at an elevation of about 1,000 meters in the Karoo area of The arid northern Cape Province, about 75 kilometers northwest of Carnarvon, with distant stations in Botswana, Ghana, Kenya, Madagascar, Mauritius, Mozambique, Namibia and Zambia. On the 10th of March 2012 it was reported that the Square Site Advisory Committee had made a confidential report in February that the South African bid was stronger. The final decision on the site by the project's board of directors was expected on the 4th of April 2012. However, a scientific working group was set up to explore possible implementation options of the two candidate host regions, and its report was expected in mid-May 2012. On the 25th of May 2012 it was announced that the SCAR will be split over the South African and African sites and the Australia and New Zealand sites. While New Zealand remains a member of the SCAR organization, as of 2014 it appears that no SCAR infrastructure is likely to be in New Zealand. Precursors, pathfinders and design studies. Many groups are working globally to develop the technology and techniques required for the SCAR. Their contributions to the international SCAR project are classified as either precursors, pathfinders or design studies. Precursor facility, a telescope on one of the two SCAR candidate sites carrying out SCAR-related activity. Pathfinder, a telescope, a program carrying out SCAR-related technology, science and operations activity. Design study, a study of one or more major subsystems of the SCAR design, including the construction of prototypes. Precursor facilities, Australian SCAR Pathfinder. The Australian SCAR Pathfinder, or ASKAP, is an $100 million project to build a telescope array of 36 12-meter dishes. It will employ advanced, innovative technologies such as phased array feeds to give a wide field of view. ASKAP is being built by CSIRO at the Murchison Radio Astronomy Observatory site, located near Buladi in the Midwest region of Western Australia. All 36 antennas and the technical systems were officially opened in October 2012. Meerkat is a South African project to build an array of 64 13.5-metre diameter dishes as a world-class science instrument, and also to help develop technology for the SCAR. Cat-7 of 7-dish engineering and science testbed instrument for Meerkat, near Carnarvon in the northern Cape Province of South Africa, is already up and running. The full Meerkat array is expected to be ready by 2015-2016. The dishes will be equipped with a number of high-performance single-pixel feeds to cover frequencies from 580 MHz up to 14 GHz. Murchison Widefield Array. The Murchison Widefield Array is a low-frequency radio array operating in the frequency range 80 to 300 MHz, also under construction at the Murchison Radio Astronomy Observatory site in Western Australia. Pathfinder's aperture tile in focus, very long baseline interferometry, electronic multibeam radio astronomy concept, Merlin, expanded very large array, long wavelength array, SCAR long-low prototype, NENUFAR, Allen Telescope Array. The Allen Telescope Array uses innovative 6.1 meters offset Gregorian dishes equipped with wideband single feeds covering frequencies from 500 MHz to 11 GHz. The 42-element array now in operation is to be extended to 350 elements. The dish design has explored methods of low-cost manufacture. LOFAR, a €150 million Dutch-led project, is building a novel low-frequency phased aperture array spread over northern Europe. An all-electronic telescope covering low frequencies from 10 to 240 MHz. It came online from 2009 to 2011. LOFAR is currently developing crucial processing techniques vital to the SCAR Design Studies Aperture Array Verification Program. Canadian SCAR Program. Preparatory study for the SCAR Square Kilometre Array Design Studies Electronic Multibeam Radio Astronomy Concept Best Data Challenges. The amount of sensory information collected pose a huge storage problem and require real-time signal processing to reduce the information to relevant data. In mid-2011 it was estimated the array could generate an exabyte a day of raw data, which could be compressed to around 10 petabytes. Technology Development Project. The Technology Development Project, or TDP, is a $12 million project to specifically develop dish and feed technology for the SCAR. It is operated by a consortium of universities led by Cornell University and was completed in 2012. Timeline and funding. The SCAR was originally conceived in 1991, with an international working group set up in 1993. This led to the signing of the first Memorandum of Agreement in 2000. Considerable early development work then followed. This culminated in the commencement of pre-SCAR in 2008, leading to a full SCAR design in 2012. Construction of Phase 1 will take place from 2018 to 2020, providing an operational array capable of carrying out the first science. Phase 2 will then follow for completion in 2025, providing full sensitivity for frequencies up to at least 14 GHz. The SCAR is projected to cost €2 billion. This includes €650 million for Phase 1 completing 2020. The funding will come from many international funding agencies. The SCAR and the European Extremely Large Telescope are the two flagship facilities for ground-based astronomy in the future. They were formerly equal high-priority projects in the ASTRO and EET roadmap for European astronomy, but the EELT is now mostly funded. Project risks. Potential risks for priority astronomical sites in South Africa are protected by the Astronomy Geographic Advantage Act of 2007. Put in place to specifically support the South African SCAR bid. It outlaws all activities that could endanger scientific operation of core astronomical instruments. In 2010, concerns were raised over the will to enforce this law when Royal Dutch Shell applied to explore the Karoo for shale gas using hydraulic fracturing, an activity that would have the potential to increase radio interference at the site. An identified remote station location for the Southern African Array in Mozambique was subject to flooding and excluded from the project. Despite the SCAR Site Selection Committee technical analysis reporting that all African remote stations could implement flood mitigation solutions, Australia's first radio quiet zone was established by the Australian Communications and Media Authority on the 11th of April 2005, specifically to protect and maintain the current radio quietness of the main Australian SCAR site at the Murchison Radio Astronomy Observatory. In February 2012, a former Australian SCAR committee chairman raised concerns with South African media about risks at the Australian candidate site, particularly in terms of cost, mining interference and land agreements. SCAR Australia stated that all points had been addressed in the site bid. During 2014, South Africa experienced a month-long strike action by the National Union of Metal Workers, which added to the delays of the installation of dishes. The plan was to have 6 dishes operational by November, but only one Meerkat dish stands on the Karoo site in the Northern Cape. The largest risk to the overall project is probably its budget, which up until now has not been committed.